Hello everyone and welcome to my presentation on Hoffman coding. Today we are going to deep dive into what this technique is, how it works mathematically, how it compares to other compression methods, its pros and cons, and finally where it is actually used in the real world. Let's get started. At its core, Hoffman coding is a highly efficient, lossless data compression algorithm. When we talk about image or data compression, our main goal is to reduce the amount of data required to represent information by removing redundant data. Hoffman coding specifically targets what we call coding redundancy. By utilizing a variable length coding scheme instead of giving every symbol a coding of the same length, Hoffman coding assigns shorter binary codes to highly probable symbols and longer codes to less probable ones. What does this guarantee? By generating a prefix free code, it ensures that the data is encoded unambiguously and optimally without losing any information. So, how do we actually construct a Hoffman tree and encode our data? The algorithm is quite elegant and follows a systematic approach. First step, the probability cascade. Sort the probabilities. First, we list all our symbols and sort them in descending order based on their occurrence of probabilities, based on their probabilities of occurrence. Building the tree architecture. Step 2, that is, combine the lowest probabilities. We take the two symbols with the lowest probabilities and combine them to create a new node. We then add the probabilities together to get the value of this new node. Resort and repeat. We place this newly combined probability back into our list, resort it to maintain descending order, and repeat the process of combining the two lowest values. We continue doing this until all probabilities merge into a single node with a value of 0.1, 1.0. Step 3, assigning pathways. That is, assigning binary values. Next, we can assign binary digits to the branch. For example, we can assign a 0 to the higher probability branch and a 1 to the lower probability branch at each node. Step 5. Trace the code word. Finally, to find the specific code for any symbol, we trace the path from the root of the tree on the right back to the original symbol on the left. The verdict. Once we have our code, we can calculate the overall efficiency by finding the average length of the code word, which is the sum of the lengths of each code multiplied by the respective probabilities. Now let's see how Hoffman coding stacks up against other compression techniques compared to lossy compression. Methods like vector quantization map data into smaller code blocks, sacrificing some real quantitative visual information to achieve massive compression ratios like 60:1. Hoffman coding is strictly lossless. Every single bit of the original data can be perfectly reconstructed. Let's compare it with run length encoding. Run length encoding simply looks for consecutive sequences of redundant data and stores them as a single value paired with a count. While RLE is great for simple and repetitive data like black and white graphics, it can actually increase the size of the file of complex images. Often coding, on the other hand, is purely based on the statistical frequency of symbols, making it much more adaptable to varying data. Another more algorithm is arithmetic encoding. Like Hoffman, arithmetic coding is a lossless variable length technique. However, instead of assigning a specific binary code binary code to each individual symbol, arithmetic coding maps an entire sequence of symbols to a single unique fractional number between 0 and 1. Let's look at the pros and cons of using Hoffman coding. Advantages: optimal and lossless. It provides an optimal prefix code, meaning the original data can be reconstructed exactly with zero information loss. Effect, efficient redundancy reduction. It is incredibly effective at removing coding redundancy by mathematically guaranteeing the shortest average code length for given set of probabilities. Disadvantages: require prior probability knowledge. To build the tree, the algorithm needs to know the exact probability or frequency of every symbol in advance. Vulnerability to error. Because the codes are variable in length, a single flip bit during transmission can corrupt the entire subsequent decoding process since the boundaries between symbols will be lost. Finally, where do we see often coding in our daily lives? Communication system. It is a fundamental technique used in modern digital communication systems to encode our source symbols efficiently before transmission. GPG compressions you use often coding every time you take a photo on your phone. In the JPEG compression standard, the image first goes through a discrete cosine transform DCT and quantization. After data is processed, Hoffman coding is used as a final entropy coding step to pack the resulting data as tightly as possible before it is saved to your disk. In conclusion, Hoffman coding remains one of the most critical algorithms in computer science. By cleverly exploiting the statistical probabilities of data, it allows us to store and transmit information effectively without losing a single drop of data. The enduring legacy of Hoffman. Developed in 1952 as a term paper, Hoffman coding remains an undisputed triumph of information theory. By simply recognizing that unequal data deserves unequal space, it lifted the weight of the digital world, proving that the most elegant mathematics is often the most enduring. A foundational algorithm that decides later still governs the architecture of the global efficiency. Thank you.